Greetings, calculus students. This is Mr. Myring coming to you with another video. In this video, we will focus on how we estimate the definite integral graphically. So looking at a graph, what can we do to estimate that area underneath the curve, which is what the definite integral talks about. So, simple, straightforward question. Estimate the area underneath the curve on A to B if A equals 1.5 and B equals 7. All right, so the reason I say it's simple is because it just says, what is that area underneath the curve? So here's this region. It's kind of shaded a little bit yellow, but that's the region that we want to be finding that area underneath. And it tells us what those values are. So way we do this is the way we go back to when we found area a long time ago when we first learned what area was. You count up what those squares are underneath. So you have your curve. When it says under the curve, we always mean beneath it and connected to the x-axis. We don't go down forever. It's just within this region between the curve and the x-axis. So as we count up those squares, you can count every single one by one, or you can try to simplify it a little bit. For instance, I know that this is 11 across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is 4 up. So I can make myself a little square, a rectangle rather, here. That is 11 by 4. So I know that there's 44 squares here. That's a good start. Knocked off quite a bit. And then you can count all the full squares. That's the way I like to do it. I'm going to count this as a full 1. And this is 1, 2, 3, 4, 5, 6, 7, 8. So those are all full squares there. There's another one right here, makes that 9. This one isn't quite full, but I'm going to say this one is more full. So now there's still 9 full squares. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to say that this one is 0.75 because that's what we do next. We go through and say, okay, well, what about the ones that aren't a full square? How much you want to say? And it's just an estimate, of course, so give it your best guess. I think that one's 0.75. I think this one right here is 0.5. This one here is also 0.5. These two together make 0.5, and these two together make 0.5. Right, I know it's hard to tell, but when you're looking at a grid, it'll make more sense yourself one sitting in front of you. So you just kind of guess how much of this square is there. I'm saying that is about 0.5, and then this amount and that amount together make about 0.5. And now we've looked at all the squares that are underneath, and so we're going to count them all up. So we had 44 to start in that rectangle. I had 9 over here and 1 over here. And now let's put together the halves. This half and that half together make 1. So do these two halves make another one, so that's another 2. And then you have that final 0.75 hanging out there. So you add them all up. 44 plus 10 is 54. 56, so you get a total of 56.75. Now, what a lot of students would do would just be done right there. They'd say 56.75 and be done. But we have to be careful because this isn't the final answer yet because of the information you're given. This is 56.75 squares that are underneath this curve. And so the question is what do those squares actually represent? And they can represent, or two things can happen with that square that you have to consider. So first of all, what is that square? What is one square worth? That's a question you have to ask yourself. As in, what is this thing? We were told that A is actually at 1.5, and we were told that B is actually at 7. So that means that each one of these width is 0.5, because here would be 1, 2, 3, 4, 5, 6, and 7. Okay, so each of those is width of 0.5. So how much is one square worth? So I don't want to count it here because I've already messed all those up with some markings, but I can look at this square over here and say, all right, well, this dimension is 0.5 of a unit because that's half of it. Now, we aren't told any information about the y-axis. That's something that you have to be careful about. Sorry about that. I didn't see that was out. So you do have to worry about what's going on the y-axis. But since we're not told the information, we can assume that it's going to be the same scaling as what's on the x-axis, which means that this is also 0.5 units. So what is 0.5 times 0.5? Well, one square is going to be that 0.5 times 0.5, which is actually going to be worth 0.25 or 0.25 of a unit. So even though we have 56.75 squares, that 56.75, you actually have to multiply that by how many units it's actually going to get you. So 56.75 times 0.25 equates out to 14.1875. So that would be then your total number of units in here. And that would be the second question. The second question is, what is the unit that you have to answer? Now, this question, as written, does not have any context. It's easy for me to give it. If it doesn't have any context, then you can just say units and be done with it, right? But in this case, let's say there was a context. Let's say this was actually an acceleration question. So this function f of x is actually giving you the acceleration of some object with respect to time. So acceleration, let's say we're measuring that acceleration in feet per second squared. So feet per second squared, which means here on the x-axis, our independent variable is going to be seconds. So that 1 square now, the unit has to be something you consider. When we were working up here with the 0.5 times 0.5, that now you're going to have 0.5 seconds times 0.5 feet per second squared. What did we do to get the 0.25 units? Well, we multiplied them, so that's what you're going to do with the unit of each of the dimensions. You multiply those as well. So 0.5 seconds times 0.5 feet per second squared, seconds times feet per second squared. The squared cancels out with the seconds, and so really this is then 14.1875 feet per second. And that would be the final answer for what the area underneath the curve is. Now, something that's going to be extremely important for us as we go throughout this entire course is, what does that value actually mean? And we're just starting with that understanding now, but it will be something that we will work with a lot. And so we'll start with it right away. And so what this is, the definite integral tells you the total change. The definite integral always will tell you what the total change is in your object or in your context. So it's equivalent to the total change. That's something that's going to be over and over and over as we go through our problems. So I would say that there was a total change. Go ahead and use that right in your statement. In velocity between, use your units on that x-axis that we had for our A and B. T equals 1.5 seconds and T equals 7 seconds of that total 14.1875 feet per second. Total change in velocity of that amount. So that's in a nutshell how we estimate the area underneath the curve. The two things you have to be careful with is, what is your square actually worth as far as the scaling? So that should be easy just by looking at the scaling on the x and y axis, and then finding your actual unit is, and that would be by actually multiplying. Area is a multiplication type of problem, and so you multiply your units to figure that out. Thank you.